Yeah, please continue.
Picking up from request node, let's do a concrete flow. Say CPU 0 needs address 0x8000. The pipeline hits the load store unit. The cache controller says miss. The request generator forms read shared, adds TXN ID, source ID, sends it out. Then it waits in the outstanding transaction table for Snoop or data. Credits limit how many outstanding packets can be in flight so buffers don't overflow. If a Snoop arrives, the cache controller checks ownership. If it has the line dirty, it may respond with data. Else, it invalidates an app. When data returns on the DAT channel matched by TXN ID, it forwards to the cache. CPU 0 completes the load. That's the basic request node. Loop. Try narrating that flow yourself, step by step, to really internalize it.
Okay, yeah, let's first try to understand the state change, right, with respect to
Mm-hmm.
C, etc.
Right.
Um, can you just give a brief about it,
Checking.
and
Mm-hmm.
we'll make sure that we understand that concept.
Definitely. Good place to slow down. If you understand the cache state machine, almost every KI transaction becomes intuitive. So we'll start with cache coherent states before mapping to opcodes. The 5 states are M modified, O for owned, E for exclusive, S for shared, I for invalid. Let's take them one at a time. Invalid is simple. The line either isn't here or is stale. If CPU 0 reads and misses, it may transition I to E or to S. Exclusive means only one cache has it. Clean and no write back needed. Modified means dirty data. Memory is wrong until write back. If another CPU reads, the home node snoops the owner. Owned is what makes Moesi different from basic MESI. Owned means you have the dirty copy, but others may read it. So you're responsible for supplying the data. Shared means many caches have clean copies. Now, if a CPU wants to write, the home node sends invalidation snoops to other caches, and then CPU 0 can upgrade to modified. For CHI, the home node orchestrates these transitions using request and snoop packets. And that's exactly what we'll diagram next time. The full Moesi state machine as used in real RTL cache controllers.
Okay, can you give the diagram of the?
Checking. Okay, here's a simplified Moesi state diagram. Start in invalid. On read miss, go to exclusive. On write miss, go to
Can you
modified.
give it as an
From
image?
checking. Absolutely. Here's a clean textual Moesi state diagram for teaching or interviews. Just imagine boxes connected by arrows. From invalid, a read miss goes to exclusive, or a write miss goes to modified. From exclusive, a local write stays in exclusive, a remote read moves to owned. From owned, a write back or evict goes to invalid. From shared, a local write invalidates others and moves to modified. From exclusive, a local write stays in exclusive. Remote read keeps it in owned. For a KI system, imagine CPU 0 in modified. CPU 1 sends read shared. The whole node snoops CPU 0. Data is forwarded on the DAT channel, and the result is CPU 0 becomes owned, CPU 1 shared. Memory still stale. For writes from shared, the home node sends invalidation snoops to other sharers, then CPU 0 moves to modified. These are how the good art versions for RTL cache state machines, and we'll expand this into a full transition diagram in the course notes.
Okay, please continue with the topics. Yeah.
Picking up. Right. So now that we have the Moesi groundwork, the natural next chapter is mapping this to KI transactions. How a read, share, or write unique request moves through the request node, how the home node interprets it, which snoops fire, and where the data channel carries the cache line. After that, we'll do RTL perspectives, like tracking outstanding IDs, credits for flow control, and simple pseudo RTL structures for a request node and home node. Then we can layer in verification angles like assertions for Snoop ordering and ID matching.
Yeah, go ahead.
To map a read, CPU 0 issues read shared. Request node sends on the rec channel. Home node checks its directory. If CPU 1 owns modified, home node sends snoop. CPU 1 supplies data on DAT, then becomes owned. CPU 0 gets shared, memory remains stale. For a write, CPU 0 sends write unique. Home node issues invalidations. Once acknowledged, CPU 0 moves to modified. In RTL terms, your request node module needs an outstanding ID table, credit counters per channel, and a tiny state machine to handle Snoop responses. The home node RTL adds a directory RAM, Snoop scheduler, and ordering logic to preserve coherency. For verification, assert that every transaction ID eventually retires, no orphan snoops, and data returns match request IDs. That's how you'll prove the design is sound.
Okay, yeah, continue.
Next, we can apply this to waveforms. We'll spot rec, snip, DAT packets, match IDs, and observe state transitions cycle by cycle. If you want, we can also draft a tiny pseudo RTL snippet for a request node to show outstanding ID tracking in practice.
Sure, go ahead.
All right. Picture a request node block with three key pieces: a request generator that forms packets with opcodes, address, TXN ID, source ID, an outstanding transaction table, essentially the small RAM or content addressable table tracking all in-flight transactions, and a credit manager to throttle how many packets are in flight. When the CPU pipeline hits a cache miss, the generator checks credits, assigns a transaction ID, pushes the packet into the rec channel FIFO, and logs it in the table. If a snoop arrives while waiting, a small state machine in the RN decides to supply data, invalidate, or stall. When data returns with a matching TXN ID, it forwards to cache, marks completion, frees the ID, and credits. That loop is the heartbeat of a KI request node. Master that, and the waveforms will start to feel obvious.
Okay, please continue.
Moving on, we can step into the RTL perspective for the home node. Think of it as three cooperating blocks: a directory RAM, a Snoop scheduler, and an ordering controller. If the directory RAM tracks who owns or shares each line, the Snoop scheduler sequences invalidations or data requests without breaking ordering rules, and the ordering controller enforces coherency rules across multiple in-flight transactions. A simple pseudocode flow might be: on request, lookup directory. If modified elsewhere, schedule Snoop. Wait for Snoop response, then grant data. On RTL, you'd model that with a state machine plus request and Snoop FIFOs. For verification, add assertions like no orphan transactions, IDs retire cleanly, credits never underflow, Snoop responses align with directory state. That's the core proof strategy.
Okay, please continue.
Great. Next, let's actually walk through a waveform style transaction verbally. Picture time on the x-axis, signals on the y-axis. At T0, CPU 0 asserts rec opcode read. At T1, home node sends snip to CPU 1. At T2, CPU 1 responds with date. Transitions to owned. At T3, CPU 0 records completion, retires TXNID, releases credits. No orphan transactions, ordering preserved. That's what to look for in waves. If you want, next, we can script a tiny system Verilog skeleton for that RN behavior.
Okay, sure.
Checking. Great, let's go to RTL implementation details. So request node microarchitecture. The CPU pipeline talks to the cache controller. On this, the request generator builds a packet, gets a transaction ID, checks credits, enqueues to the rec FIFO, logs it in the outstanding table. While waiting, the Snoop handler may need to supply data or invalidate a line. When a DAT packet arrives, it looks up the TXN ID, forwards data to the cache controller, frees the table entry, returns a credit, and wakes the CPU. In RTL terms, model it as a finite state machine with idle, allocate ID, send request, wait response, handle Snoop, complete. Next, we'll do a similar deep dive for the home node internals.
Yeah.
Continuing. Checking. Excellent. The home node is the most important block in a CHI system. Think of it as the coordinator that enforces coherency across the entire system. High-level RTL view. Incoming rec channel enters request decoder, parses opcodes, addresses IDs, and routes by opcode. Then a transaction tracker table, as with RN but more complex. Directory RAM to store ownership and sharer info. Snoop scheduler deciding who to invalidate. Memory interface when no cache owns the latest copy. Data router handling incoming data. Response generator finishing transactions. The hard part is the ordering controller, making sure simultaneous transactions obey KI's ordering rules. That's the centerpiece RTL challenge for the home node.
Okay.
Let's do the home node microarchitecture at an RTL designer level. The major RTL blocks are request decoder, transaction tracker, directory RAM, Snoop scheduler, memory interface to DDR, data router, response generator, plus ordering controller. Request decoder pulls opcode and address off the rec channel. Tracker allocates an ID, directory RAM checks ownership. Snoop scheduler issues invalidation or data snoops. Memory interface talks to the DDR controller if needed. Data router handles returning data. Response generator formats completion or retry. Ordering controller enforces coherency rules across overlapping transactions. In interviews, be ready to explain how the ordering controller keeps transactions to the same cache line ordered.
Yeah, continue.
The ordering controller basically makes sure that if two transactions target the same cache line, they complete in a legal order. So you don't get one write sneaking in before a prior read finishes. It uses transaction IDs, per ID queues, and barriers when needed. So for example, two writes to 0x8000 won't pass each other. One finishes, then the next begins. That's how coherency stays correct, even with multiple clusters, accelerators, and speculative execution going on at once.
So what do you mean by clusters?
Checking. That's a good question. So if you have multiple clusters, each cluster is usually a request node. The home node keeps a directory per address showing which request nodes have a copy of a cache line. So if cluster 1 wants to write to 0x8000 while the GPU cluster wants to read it, the home node will serialize those requests with its ordering controller, ensuring consistency. So the GPU will see the newly written value, not the old one. That's how Chai scales coherency cleanly across many clusters without broadcasting snoops everywhere.
So was Snoop broadcasted as a fake site protocol?
Let me check. So in ACE, you probably mean ACE protocol. In ACE, coherency relies on broadcast snooping. So if CPU 0 requests a line, the interconnect might send snoop requests to every other CPU cluster, even ones that don't have the line. As core counts grow, that becomes noisy and power hungry. HI instead uses a directory in the home node, so only the cluster that actually owns the line gets snooped. That cuts unnecessary traffic, lowers power, and scales a lot better for modern multi-cluster SoCs.
Yeah. So this requested node kind
Mhm.
of snoops the node, and the home node then checks the directory, and then based on that, it tells back to the requested node of that particular cluster whether that
Yeah.
data is existing and it has to be changed or not. Is that correct?
Checking. Close, but two tweaks. The request node does not snoop other request nodes. All coherency decisions go through the home node. The home node checks the directory, decides whether to talk to memory or send snoops, orchestrates invalidations if needed, then completes the requesting node's transaction. So it's basically the conductor, not a bystander.
Okay, let us say there's a transaction which is coming from the CPU. It has to reach the DDR. So first, the CPU sends transaction. So that comes from one of the request nodes, right? Or like, what do you mean by different request nodes? Uh, right. So once the request node data comes, that goes to the home node, and based on if the data is got changed or not, it comes back.
Checking. Right. So the flow is basically as you said. CPU in a request node issues a read or write. The home node checks its directory. If no cache owns the line, the home node may fetch from DDR and return it. But if another request node already has it, the home node snoops that owner, gets the data back, updates the directory, and forwards it to the requester. The request node itself doesn't know the global picture. It relies on the home node like a central catalog, kind of like a librarian checking whether a book is in the archive or already borrowed by someone else. That central catalog role is exactly why the home node exists in a SHI system.
So the request node is basically the cache, right? Different caches we have.
Yes, think caches grouped with their cores as a request node. The Rn is that cluster acting coherently. Inside are the L1, maybe a shared L2, and the logic to package SHI requests. When the CPU misses an L1, the Rn forms a read or write request to the home node, then lets the home node coordinate snoops or memory access. The request node itself doesn't talk to DDR directly. It waits for the home node to return data. Then it fills its cache and resumes the CPU. So different caches appear as different request nodes. The home node arbitrates between them, keeping everything consistent. That is the core RNHN interaction you'll debug in Waze and implement in RTL.
So basically,
Mhm.
what do you mean by request node? It is the cache along with core. What do you mean with core? And can you explain more in detail? What do you mean with core and cache?
Checking. Great place to slow down. So a CPU core is the part that runs instructions. It doesn't touch DDR directly. It goes through caches, which are small, fast memories that hold recently used data to avoid slow DDR trips. A CPU cluster groups several cores, each with L1 caches, maybe a shared L2. The RN wraps that cluster with HI logic like request generators, credit managers, outstanding tables, and Snoop handlers. When a core misses in cache, the RN creates a shy request like read shared, sends it to the home node, and waits for data to come back. So the RN is more than just a cache. It's the cache plus all the plumbing needed to communicate coherently with the interconnect.
ARM is basically the CPU core, right? CPU is split into multiple cores. That 8 core, 4 core, that is the core you're telling about. And along with the core, we will also have the cache inside that. So that together, RN is equal to the CPU core plus the cache and whatever
Hmm.
logic is required to interact with the core. Is that correct?
Yeah.
Uh,
Checking. Yes, that's very close. But RN is not just the core. It's the entire coherent block, usually a CPU cluster with its caches and the SHI interface logic. The cores don't know CHI exists. The cache controller and RN logic handle that. So in an SoC with 8 CPU cores, you might have 2 request nodes, each representing a cluster of 4 cores. When a core needs data, the RN logic turns that into a SHI request to the home node. It's more accurate to say RN equals the whole coherent agent, CPU cluster plus caches plus SHI logic, rather than just core plus cache. That distinction matters for RTL scope and for understanding what SHI actually talks to.
So, like, why do we have like multiple cores instead of just a single core?
Checking. The reason is that workloads grew beyond what a single CPU core can do efficiently. Early on, one core handled everything, but as demands grew, we moved to multi-core for parallel work. Caches keep each core fast, but then we hit the coherency problem, keeping all cores seeing the same data consistently. Protocols like 8CE and JHI solve that by organizing request nodes, home nodes, and directories so everything stays coordinated. Without that, Core 1 might read stale data while Core 0 already updated it, which is disastrous. That's why scalable coherency became essential as we went from single core to multi-core to multiple coherent request nodes.